Now that we've discussed what a vector space is, we're going to look at the concept of subspaces. So if we look at how we define a subspace, if I've got a real vector space V, then a subset of that set V, because remember a vector space is a set with two operations. So if I've got a subset of my vector space V, then that set is a subspace of V if it is again a real vector space under the same vector addition and scalar multiplication defined and in V. So what we're looking at is a vector space V. Then I look at a smaller set, a subset. It could be smaller. W, a subset of V, the same scalar multiplication, the same vector addition. If that set W is again a vector space, then we call it a subspace. So just to remind you, all those axioms linked to being a vector space will then have to be adhered to. But what we're going to see is that if I know that V is a vector space, then we don't necessarily have to check all those axioms to show that W is also a vector space, and that's where we're going to. So let's just investigate that a bit further. Let's look at an example. Let W be all the coordinates x, y, so it's a subset of R2 with specific restriction where ax plus by is equal to 0 for some a or b in the real numbers. So for example, we can look at 3x plus 4y equal to 0. So straight lines through the origin. So we pick one straight line, we pick an a and a b, but we're just using a generic a and b here. But for a, b real numbers, that is what my subset look like. And we define scalar addition and multiplication in the standard way as we do in R2. So now the question is, if I want to show that this set W is a subspace of R2, we said, well, it must again be a vector space. So it must adhere to all the vector space axioms. And so if I pick U, V, and W, if I pick three vectors in W, then let's just look at some of those axioms. We're not going to formally prove them one by one. We're just going to get an idea of what we're looking at here. If I've got three elements that are now in W, then if I know R2 is a vector space, I know because they're in W, those elements, those vectors, are in R2. There's a bit more of a restriction for them to be in W, but they are in R2. So what holds in R2 must hold for those. So those are all vectors in R2, which is in a vector space, which means we're not looking at that first axiom. We'll get to that. But U plus V plus W is the same as U plus V plus W. That is inherited from R2 because all of three of those are in R2. All right? The commutativity is inherited from R2. All of these axioms are just inherited from R2. So there's a couple to look at. The closedness, we will look at those separately, but let's look at this element 0 is in V. The question is it also in well, in this case, we're looking at R2, because then this will be inherited. And if the negative is also in R2 in the set W, then this will also be inherited. So we'll think about that for a bit, but let's first look at these two closure axioms. We want, for two elements in W, I want to see, will U plus V also be in W? That's what we're looking at. Will that be true? If I add two elements, will they again be in W? Well, if U is equal to x1, y1, then I know that ax1 plus by1 is going to be 0. If V is x2, y2, I know that ax2 plus by2 is going to be 0. So what happens if I add U and V? Well, U plus V will be addition in the standard way, so it'll be x1 plus x2, y1 plus y2. So will this condition hold? Well, what happens if I take A times x1 plus x2? I know, and add to that B times y1 plus y2. I want that to be 0. Is it 0? Well, that is ax1 plus ax2 plus by1 plus by2. And I know from the fact that they're both in W that will just, by reordering, I will end up in 0. So U plus V is an element in W. So W is closed under addition. So let's look at scalar multiplication. If I look at some scalar, if K is a real number, if K times U, what would that look like? Kx1, Ky1. So what we want to look at is A times Kx1 plus B times Ky1. Well, if A times Kx1 plus B times Ky1, I want that to be 0. But let's see what it is. Well, we can take K out. Multiplication is associative and commutative, so that's K times Ax1 plus By1. So it's K times 0, which is 0. So that is again in W. So this set W is closed under scalar multiplication, and it's closed under vector addition. All right, now the 0 will also be in W. If W is a non-zero set or non-empty set, then I can find 0 in W. Similarly, we can find the negative in W of any element, and it's closed under addition. So what it comes down to is the axioms that I want to check is the closedness. And I want to check that this set W is non-empty. Because if it's an empty set, then it can't be a vector space. So we want a non-empty subset for which addition and multiplication is closed, and then the other axioms are all inherited from the bigger set, in this case R2. So what we've got is if V is a real vector space and W is a subset of V, W is a non-empty set, then W is a subspace of V if the following conditions hold. If it's closed under addition and closed under scalar multiplication. So what we have now is the situation where if I've got a subset of a vector space, I can show that it's a subspace, and with that a vector space in itself, if I show that make sure it's non-empty and I show these two conditions. That's all I need to check if that W is a vector space in its own right. We don't have to go through all the other axioms. So let's look at an example. The first two obvious examples, and you can confirm that, if I've got any vector space V, we don't have to say what it looks like. If W contains only the 0 vector, then it's non-empty. And we know the 0 plus 0 gives me 0, so it's closed under addition because 0 is in W. And any scalar times 0 just gives me 0, so it's closed under scalar multiplication. So W, in this case, the set containing only the 0 vector, is a vector space, and it's a subspace of vector space V. Or if I choose W to be the whole of V, then it's a bit redundant because W is the whole of V. V is already a vector space. So I know W is a subset of V if it's the whole of V. Therefore, it's non-empty and it is closed. So W is then a subspace of V. Let's look at two more examples. Let's stick to R2. Let's define W1 to be the set of all ordered pairs where this X and Y coordinates are greater than or equal to 0. So the first thing we want to check is if W1 is non-empty. Can I find an element in there? You can find an infinite number of elements. 0, 0, I know is in W1 because the first coordinate is greater than or equal to 0 and the second coordinate is greater than or equal to 0. So therefore W1 is non-empty. For that matter, 5, 17 is also in W1. You can find a whole list of elements. I just chose a simple one. The next thing we want to see is it closed under addition. So for U equal to x1, y1, and V equal to x2, y2. U and V in W means that x1, y1, x2, and y2 are all greater than or equal to 0. So let's see what happens if I add them. U plus V, we've got the standard addition because I'm just looking at R2 and no other additional multiplication was defined. So the standard addition is x1 plus x2, y1 plus y2. Well, I know that x1 and x2 are greater than or equal to 0, so x1 plus x2 must be greater than or equal to 0. And because y1 and y2 are greater than or equal to 0, y1 plus y2 must be greater than or equal to 0. So therefore, U plus V is an element of W1. So it's closed under addition. Let's look at scalar multiplication. Now you've got to stop and think. If I multiply, if I've got two numbers here that are greater than or equal to 0, and I multiplied with any scalar, will I again be in this set? Meaning, will those numbers be greater than or equal to 0 every time, no matter what scalar I choose? And the answer is no. And we can use a counterexample. Let's just use our scalar equal to -1. And u be equal to, well, let's choose one we haven't used. Let's call it w, equal to 1, 2. Then k times w is equal to -1 minus 2, and that is not an element of this set. So therefore, w1 is not closed under scalar multiplication. And therefore, I can conclude that w1 is not a subspace of R2, and therefore not a vector space in itself. And the last example here, let's look at all coordinates that looks like this, where the y coordinate is 0, but the x coordinate can be any real number. So look at this subset of R2. So this is the whole x-axis, if you think of it like that. So firstly, 0, 0 is in W2. So W2 is non-empty. Secondly, if u equal to x1, 0, and v equal to x2, 0, u and v are elements of W2, then what happens if I add them? U plus v is equal to x1 plus x2 and 0 plus 0, which gives me 0. So this again is in W2. And if I've got any real number k, k times u is going to be equal to kx1 and k times 0, which is 0. So again, I find myself in W2. So W2 is closed under, is non-empty, it's closed under vector addition, it's closed under scalar multiplication. So therefore W2 is a subspace of R2 with the same standard vector addition as scalar multiplication. In the next video, we're going to be looking at more subspaces, examples of subspaces of well-known vector spaces.